First, let me say something. If you have any questions at all, just show up and let's process them right away. I really like if I get interrupted actually with questions so that we can drive the discussion in the direction that you guys wanted to go instead of me just reading my slides. Yeah, I'm going to talk about systemd and containers. Containers, of course, is kind of one of the hottest topics right now, and systemd is kind of the core piece of most of today's operating systems, or Linux operating systems. So my talk will basically just cover where they touch each other, and the largest part will probably be about, one very small container manager that is actually included in systemd itself, which is systemd-nspawn. Which is not that well known as Docker, but in many cases is probably equally useful. So, what we'll talk about is systemd on the host, right? So that the containers run on top of systemd. Systemd inside the container, right? So that systemd is inside the container. And the third topic is going to be systemd-nspawn as actually the container manager. So the first topic is systemd on the host. Systemd on the host brings a couple of components along with it that make it possible that you can integrate containers right as a concept into the rest of the operating system. These components are systemd, machined, and machine control. Any container manager that exists can integrate with that and can get some benefits because these two, like systemd machined is this very small local daemon, and machine control is a small command line program. These two components make it possible that the concept of a container is actually known to the rest of the operating system. That opens up a number of functionality. First of all, machine control, that command that I'm talking about, actually has a couple of commands. Machine control terminate to terminate a local container, machine control shell to get a shell, machine control login to get a full login prompt with username and password. This, of course, isn't too interesting because the container managers there are, LXC, Docker, and these kind of things, offer this anyway, so that's not too interesting. But it gets more interesting. If your container manager, Docker, LXC, and whatever else, integrate with this, and most of them actually do, then you get functionality in journal control, system control, login control, and systemd run. Now, I'm not sure how well you all know systemd. This talk isn't supposed to be about systemd, so I'm not going to give you the introduction about this. But I will give you a very short overview about these four commands. Journal control is the primary command how on systemd systems you can introspect the logs of the system itself or specific services and allows filtering and things like that. The container integration the systemd provides also makes it possible that you can look at the logs generated of any specific container. For that, we have the journal control -m command where you just specify container name, and then you get instead of getting the host logs, you get the containers logs. System control, for those who don't know, is the primary command how you actually interface with systemd itself, meaning with systemd, the service manager. System control -m is again a way how you can execute a specific command not on the host, but on a specific container. Right? So, for example, with system control, you would execute something like system control start mysql.service. If you type system control -m, some container name start mysql.service, then the same operation is executed, but instead of on the host, in a specific container. Similar, login control is something that's probably not too relevant on servers, but definitely on clients. It gives you information about locally logged in users and sessions and seeds and these kind of things. Login control -m gives you the same for a specific local container. Systemd run is a very useful tool in systemd. It basically allows you to run something as a system service, but instead of actually having to write a service file for that, a unit file for that, how we call that in systemd, it allows you to run a service just from the command line, simply by specifying a couple of parameters, which is really, really useful for many cases on the local system, but it's actually, because of systemd run -m again, allows you to run a specific command, not in the host, but in any local container that's running, that registers with machined. So that's already pretty useful. A couple of other things there are as well, like for example, NSS my host name is sorry, that's actually a typo. It's supposed to say my machine. Sorry for that. So NSS my machines is actually a pretty useful tool that basically says if you have a container locally running and it has a name and it has networking, then NSS my machines will actually make sure that you have name resolution towards that container working locally. Name resolution meaning that the host name of that, like the name of the container, can be resolved by the libc function get adre info and get host by name, which basically means that you can write ping and the name of the container, and the right thing happens that this always will resolve to the locally running container. All of this works for any container manager that registers with it. That's pretty much all the popular ones you know. They actually, like, this is not supposed to be complete because there are many more integration points. Like, for example, one that just comes to my mind is PS, right? Everybody here knows the PS command on Unix, which shows you the process list. A container manager that integrates with this will have a column of its own for the processes owned by a container that show to which container this belongs. That's actually really useful because if you have a lot of containers and you look at PS, you see a gigantic tree, right? Because you see the host processes plus the processes of each container. And if you have an extra column that tells you, okay, this belongs to the host, and this belongs to that container, and that belongs to that container, that's actually pretty useful. There are many more integration points like that. Like, for example, the GNOME tools, like the UI tools, integrate with that as well. So if you use GNOME System Monitor or something like that, you also get this column. And quite a few others. So this is in no way complete. The message that I really want to get across here is that these integration points exist, and that the concept of what is a container, simply by registering with this machine machine control thing, it actually becomes the concept of the operating system itself, so that containers are not just something you put on top, but are actually known as a concept to everything else in the operating system. Yeah, and it works for any container manager that registers with it, like LXC and Docker and these kind of things. That was the first facet I wanted to cover. And again, if you have any questions, totally interrupt me. Next one, systemd running inside of the container. Note that this running systemd inside of the container basically means that you have a host that runs systemd, but also as many containers as you have run systemd as well. So every container in this model kind of is like a system of itself, right? It feels, if you do this, it feels more like you would run a couple of VMs, right? Like of more complete operating systems on top of another operating system. This is not, by the way, the Docker model, right? The Docker model, they generally try to focus on microservices so that you do not run another init system inside. But even they allow to doing this because it usually, like, as soon as you want to run more than one service inside a single container, usually you need something like a service manager because you have multiple services to care for. Anyway, so systemd inside of the container. There are a lot of integration points that if systemd is in the payload, it can take benefit of what the host provides. Again, like basically systemd in the container will just work. Most of the integration points you will probably never see, but I put them on the slide here anyway so that you know that they exist. One of these things, for example, is you can provision the machine UUID. The machine UUID is something that has been added like with systemd. It basically is a UUID, like a unique ID that is randomly assigned to each system, so which can be used to identify a specific system. With using the container integration that systemd provides when running inside of the container, the container manager running on the host can actually pass along the UUID to use for that instance. This is relatively useful because it allows using the same, like many container managers actually assign these, like libvirt LXC, for example, assign UUIDs anyway. And it's kind of nice if the UUID used from outside to identify that container is actually also the UUID used from inside to identify itself. So you can do that. Systemd, when run in the container, will automatically detect that it runs inside of a container and will open a login prompt on the local console, right? This is actually a pretty useful feature, and it sounds pretty obvious, but it traditionally is not, because traditional distributions the traditional init systems, they will start a login prompt on dev-tty1, dev-tty2 in these, like the virtual console. But the virtual console does not exist in a container. So yeah, it will just automatically do the right thing so that you don't actually have to think about anything, and you still get a login prompt that you can log into if you want to. Another integration point is socket activation. Not sure how many of you know the concept of socket activation. It's actually something that systemd made popular again, I guess, in a way, on Unix. It's this concept which allows you to say, I want to run a network service, but instead of running it all the time, and thus always consume memory, consume CPU, I just want to run it the moment where a connection comes in. This is immensely useful. This is immensely useful. Like, let's say you have a big system and you want to run a lot of custom applications on them, but you want to reach a gigantic density with that. By using socket activation, you can come to a system where you basically say, okay, I'm serving this and this and this and this and this, but actually you're not running any of it until the point where they're actually requested. Like, this is actually pretty useful. Like a company that has been working with us, they have this thing where you have on the website you can click on you want to demo Drupal instance or something like that. So it's very, very easy for people who use that website to allocate their own Drupal instance, and they get them for free. So most of them will do that, and then they get an example Drupal website, and they can play around with them. But almost all of them, like 99%, will never actually come back to that website again anymore because they just wanted to test it. So this company has this thing where about 1% of the website that they host are actually used and stay around. But 99% are just these testing things where somebody clicked on a button and wanted to see how it works. Now, with something like socket activation, you have this nice concept where you can say, yeah, we run 100,000 websites, but actually you just run 1% of them, and all the other ones are just hanging around there and are activated only at that time where they're actually requested. Systemd, when running in the container, now is open up for socket activation so that the container manager running on the host can nicely activate the container and pass the connection socket that this connection was seen on to the container, and then is distributed to the service running inside of it. So you basically get this chain where the host listens on port 80, for example. When a connection comes in on port 80, it will activate the entire container. That socket, the port 80 socket, is passed on to that container, and then systemd running inside of that container will pass it on to the HTTPD instance or whatever is running in the container to actually process the thing. Yeah, it's actually really, really useful, and these are actually some of these things where when systemd is running inside of a container, you actually get a big benefit over running things on a VM, because on a VM these things are not that easy, because you cannot just pass a socket through, because a socket is an operating system concept, and if you have virtual machines, then they don't share an operating system, so they cannot share these concepts. And again, if any one of you has questions, completely interrupt me. I know that I speak pretty fast, by the way, so if I speak too fast, just say something. Nobody has any questions. Sorry? That's a very good question. So I'll repeat the question. By the way, there is a microphone, so if somebody has to say something longer, let's do that with that microphone. But your question was what the delay is with socket activation if a connection comes in. And that really depends, right? A container is usually pretty fast to start up. So on my demo, like when I test this, I usually get 100 milliseconds or something to boot up a container. And that's the maximum, right? That's an absolute worst case thing. But it really depends what you actually run in the container. If you just run HTTPD, it's really cheap, right? But if you run your database there, it might take longer. So if you want to do socket-activated MySQL, knock yourself out, but of course it won't be as fast. But usually it's going to be good enough because most people, because it's only going to be on the first activation, right? Like the first time something requests, and that's going to be up, and then it's going to be fast. I'm not actually sure about, you said Docker, right? I'm not actually sure that Docker is already capable of making use of the socket activation, but the other ones are. But that really depends. Like, actually, the system, like the container itself has to figure out when it's idle right? Because you can never know that from the outside. And only when the container itself figured out that it's idle, it can exit. Right, so the background of this is like idle detection is actually a topic one could probably do an entire talk about. It's about the container needs to know when it has all work done that it needed to do, and only then can exit. And that's something that systemd will not solve for you. It will give you hooks to make that easy, but it's actually, like for example, HTTPD or something has to figure out when it's idle and can exit. And then you can tear down the entire container if you're ready for that. But there's no generic concept for automatic exit on idle for containers in place.
Hey Lennart, a slightly broader question. So does systemd expose an application programming interface like libcontainer for creating network namespace or C groups and things like that?
Yes, it does. Not for network namespaces, but the Linux kernel does that, but for C groups we do. So systemd has a very comprehensive dbus interface. Okay, let's not say comprehensive because there are parts missing. Like the problem with C groups, for example, is that the kernel API is not very good at this moment. That's being fixed, but we only decided to expose the parts to user space where the kernel people and we are decided that it's good enough and it's going to stay that way. Like we are very conservative with exposing something to applications where the kernel isn't stable and where we know that the kernel will change because it will basically mean that in a very short time future everything will break because people use APIs that are no longer supported. But yeah, there's documentation. It's not always fully up to date, but if you Google for it, like it's a dbus interface, then you can do C groups with that and can a lot of other things with that.
One more question. If systemd on the host can detect when the connection systemd on the host can detect when the connection comes in and activate the appropriate container with appropriate service. It also can detect. When the connection closes. So, is it possible to trigger a container close then?
So it's actually not that easy. It can't really detect that. The thing is because normally, like if you have a listening socket, right? Then this listening socket is the thing that systemd takes care of, and each time a connection comes in from that, you get the incoming connection gets turned into connection socket, and that connection socket is passed off, and systemd doesn't watch that anymore, so it doesn't actually work. Okay, let's continue with the slides. So like we covered already, systemd on the host, systemd inside of the container, and pointed out a couple of integration points there. Now I want to talk about the third part, which is systemd-nspawn actually as a container manager. Now you know a lot of container managers, right? You know Docker, which is kind of the most famous that everybody's using, but there are a couple of other ones. There's Rocket, there's LXC, there's libvirt LXC, and there are a couple of smaller ones. Systemd-nspawn is another one, which is of course great because we always need like 10 implementations of the same thing, right? To explain this, why nspawn exists. Nspawn is a minimal container manager, right? And it's part of systemd itself. If you have systemd installed, you'll also have nspawn. Nspawn is relatively simple, right? The reason we created this was actually because we wrote systemd itself, which is an init system, and to be able to test systemd, we of course need to constantly reboot the system, right? That's at least the traditional theory, because after all, our software is responsible for booting up, so if we test it, we need to boot up all the time. Now, while developing this, we got annoyed by that we have to reboot the physical system. So the next step was, of course, to work with VMs. VMs boot much faster, and you don't have to reboot your host system all the time. You don't have to stop your Emacs, so it's already a lot nicer. But it's still not as good as it could be because containers have this advantage because they run on the same kernel. You can actually debug them. Like you can actually use GDB or strace or all the commands that exist on Linux to profile, to trace, and to debug something can actually work across the container boundary, and you can access from the host whatever the container is currently doing. So back then we thought, okay, let's use containers to make our development of systemd easier. And we started using LXC back then, and it was really, really, really complex, and a lot of work to actually get set up. And we thought, okay, let's write something more minimal that just works for us, and basically something that works like a powerful chroot, right? Yeah, everybody here knows chroot probably. Chroot is a thing where you can run a binary and have its root directory be actually just a subdirectory of the root of the host, right? And we thought, okay, containers are a little bit like that. Let's just write a minimal container manager that works like chroot and that can execute basically a directory tree or an OS in a directory tree that's lying around somewhere. And yeah, that's what nspawn is, and it's still like that, right? Like if you want to quickly boot up some operating system that you have in a local directory tree, and systemd-nspawn is the easiest tool to do that, because you just write nspawn systemd-nspawn-d and specify the directory, press enter, and there you go. You see the boot up process, and you can actually get a login prompt and can immediately log in. Like a machine control, like this command that I explained earlier, actually it integrates with any container manager, but it has special support for nspawn. Like for example, it has this command machine control start, which actually is hooked up to nspawn. So if you use machine control start, then you end up with nspawn. All the other commands work with everything else too. To make this clear, what nspawn is and what it isn't, the focus of nspawn is full OS containers, right? The focus of nspawn here is that you actually run an init system inside of it. I kind of mentioned this already, that is different from the approach that Docker is choosing, because Docker's focus is really on microservices, right? Like so that you run exactly one service inside of a container. So yeah, our focus with nspawn is, or focus number one, is actually OS containers that carry a full OS inside, including an init system. There's also a second focus, which is probably less relevant for most here, but it's also important, is that it's a basic building block for other systems to build something off. This is actually being used by Rocket. I'm not sure if you guys know Rocket. Rocket is something, it's a container infrastructure. It's pretty much the same thing as Docker, except it's not Docker. It's done by a company, CoreOS. I personally think it's much, much nicer than Docker, and I think many people think that. But then again, the mind share is clearly with Docker and not with Rocket. But yeah, I personally like it very much, of course, that nspawn is used as the backend to Rocket. So that nspawn is used by them actually as the actual container execution engine. But they're building container delivery, container updating, these kind of things on top of nspawn, that is the execution engine. Anyway, back to nspawn. And yeah, my remaining slides are really about using nspawn to run full OS containers. So this is useful often. I'm not saying that this is, like, to make it very clear, this is nothing that is supposed to be in competition with Docker, right? This is a different use case. And sometimes I'm pretty sure that any administrator will find this use case be closer to what he's trying to solve at that moment than Docker. So the basic mode of operation is you place an OS tree, meaning an OS tree is something where you have etc and bin and user and what's it all called. You place it in one directory, varlib machines foo. Foo is whatever you call the container. Then you invoke this command. I actually have the laser pointer here, nice. So I tested with this command, which is just invoking systemd-nspawn-m, and you specify foo, which is again the machine name. And there you go. You get the thing booted up and you can log into it. It's really like a VM, but it's much more integrated, much simpler. Then after you I don't know, configured it or whatever, you actually can enable it permanently by running machine control enable foo. From that moment on, it will be automatically started at the next boot. And then you can actually start it immediately as a background service by machine control start foo. That's kind of really the workflow that there is, and there's not much more about the basic mode of operation to know, right? You just have to have that tree. You can test it easily, and then you get the output on the console, and then you enable it persistently for the next boots, and you can start it directly as a background service if you like. The basic concept that we try to follow here is that full OS containers as a system service. What does that mean? It basically means that the operating system containers that we have here, that run that run their own init systems, things like that, are actually exposed like any other local system services on the host, right? So if on the host you run Apache and MySQL, but you also run 5 containers, right? Then all of these will just be showing up as individual services if you type system control and get the list of running services. So the concept really here is that there's a clear one-to-one mapping, or so that you have one container maps to one service, which again is different from how Docker exposes that, because in Docker you have the Docker manager service, whatever it's called again, and then they fork off each container from that, but the host only sees one service that's all of it. On this model is different again, because every container is its own individual service. This actually brings quite a few benefits, because the distinction between a container and a normal service mostly goes away. That is interesting, for example, for logging purposes, but it's primarily useful for resource management. Because systemd has all these properties where you can say, this service gets this much memory at max and this much CPU and things like that. And because a container and a service is the same thing for systemd, you can actually do it the same way. So you can basically say, yeah, this container gets 5 gigabytes of memory, and this one gets 3, and that service gets that stuff and things like that. You can also bind the execution together, where you basically can say, run this container, but if you run it, first start Apache, or first start MySQL on the host, or run this container, then this container when that's finished, and things like that. And you have quite a few other integration points. You can share things between containers and the host, and things like that. So the question was how we handle if it's out of memory. That's a very good question, and the answer is depends. The thing is, we use some concept of the kernel there, like the memory cgroup controller exposed that to us. And the behavior, if you run out of memory, is different in the different kernel versions. So originally, there would be an OOM killer, if you know the OOM killer, and would just kill the containers processes individually from independently from the rest. In the current kernels, it's different. It's simply that the stuff gets swapped out in a more frequently, so it will actually continue running, but it will get awfully slow if it starts allocating enough memory. But what exactly happens there is kind of out of focus for systemd, because we just provide you with the ability to configure these kernel concepts. What the kernel then does with them is a different thing. I mean, I would like to improve this actually, because what I really want is that the kernel gives me notification when a specific service uses too much memory, so that we actually can report it to the user in a nice way and react to it, like, for example, shutting down that service and only that service in a clean way. Yeah. So to make this clear, this basic concept: if a container foo is running as a system service, it will show up in the service tree as systemd-nspawn at foo.service. A little bit of background for those who do not know systemd so well. In systemd, all the services and other units that it manages always have some name, dot some suffix. The suffix specifies what the type of that thing is. For services, that's always .service. And then it has this concept that you can write have one definition of a unit that is used for many instances, and that's denoted with the at thing here. And in this case, basically it says systemd-nspawn at.service is a template that is instantiated once for each of the containers, and in this case, foo is the instance name. So yeah. So the question was whether you can create a container inside of a container. Very good question. Yes, you may. But you lose functionality. So the functionality that you lose is, or it might eventually work fully, but right now it's that the resource management is not safe. That you can, it's a security problem basically. It's not safe to allow containers to manage their own resources below what they get on the classic cgroup hierarchy and the classic kernels right now. So basically, you will be able to run containers inside of containers, but you lose resource management inside of them. So on the host, you can basically say this container gets this much CPU, but if you try that inside of the container for the sub-container, then it won't work anymore. But they're working on fixing that. So with the unified cgroup hierarchy and blah, 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 new stuff, it will eventually probably work just completely freely, that you can stack them as you wish.
Okay, machine-ctl enable will enable systemd-nspawn at machine name. But can we agree on an additional name for the .service file for the cases when you have to specify some additional
settings?
Settings
We have
in
something
the
for that.
unit file. I know that we have the dash, I mean .nspawn
Yeah.
files, but I mean the case when you have to use exec start pre or exec stop post in the unit file. So maybe.
So my recommendation to that is the systemd-nspawn add is a suggestion we make, and people can use that, right? But ultimately, there's no reason to use them. You can write your completely own unit
but
file for that.
then you will lose integration with machinectl,
No,
the start and enable.
No. The command machine controls enable and then service is exactly nothing more than a nicer way to run system control. System control enable systemd-nspawn.
Yeah.
The only benefit it really gives you is the escaping of the because this name that you specify here needs to be escaped in a certain way, and that's the only thing that it gives you. So use system control directly. You will not you lose any functionality. Everything like this, basically, machine control enable is really supposed to just make it a tiny bit easier for you, but it's not going to give you any additional features. It really doesn't. Because these OS containers are like normal services, the usual service management commands are supported. So you can start and stop them and things like that. System control start, system control stop, and so on. Of course, sometimes if you actually want to use these kind of containers, like these full OS containers, it's useful to actually get them from the internet. For that, we have a command here. I had to make the font small so it actually fits on. I hope you can see something. Basically, what you see is machine control pull raw, verify equals no, and then some URL. This basically is a way how you can download an image from the internet. In this case, it's a raw disk image. Because nspawn actually supports formats. Like I have a slide about that later. Let me find that one. By the way, we are not going to be able to do all the slides here, but that's completely okay. I was looking for this one. Systemd containers, I already mentioned that. It's completely sufficient to have this directory while machine's foo. Because Fedora images do not come with sane GPG signatures at this moment, so I had to turn that off. The irony of this is if you download an Ubuntu image with the same command, it will actually work. Which, like, I as a Red Hat guy, it's kind of weird that we support Ubuntu that better than we currently support Fedora. Don't tell anyone. Anyway, the image format that I was mentioning, it's completely sufficient if you have just a simple directory, and it will boot that up. But optional, we also support butterfly subvolumes, which are pretty much like normal directories. And the third format we support is raw disk images. Raw disk images meaning something, just a loopback thing. And nspawn will automatically dissect them, read the partition table if there's one inside of them, and mount them for the container. So it's kind of nice because you can actually, this way, you can even point nspawn to a real raw disk, like a USB stick or something like that, and will boot up the thing that's inside of it.
And now when we have ZFS in Ubuntu and Debian, maybe ZFS datasets.
So one thing that I think is very important is that nspawn is really supposed to be simple. And that basically means I have no intention to support everything that's around on the planet, right? So LXC, for example, LXC is very similar in many ways to nspawn, but LXC tries to support everything on the planet, right? Like they have storage backends like crazy. For us, it is really, I'm happy to support ZFS basically if it's in the kernel. But I don't see that coming anytime soon. So I have no problem with any kind of technology, but what I do care about, I want to have well-supported technology that has a clear future inside of the kernel. Anyway, so that's how you can get that. You basically, with this command, you download it, and with this command, systemd-nspawn-uppercase-m, you then just run what you got. And that's pretty much it. So we have not much more time. I got a lot more slides, but it's completely okay that we didn't get through to them. Like my main reason I had them is that I can fill the time if nobody of you asks a question. But since you asked a question, that's actually pretty good. Anyway, let's the few minutes that we have left, let's do that with more questions because that's much better. Well, it's a no. Like this is supposed to be simple, right? Like, and the idea is really that you can just point it to some file on the internet, and then it will download that and run it. Where that's stored, I don't really care about. That's completely out of focus. Like, I will not do server software. Systemd is supposed to be client software, and this is already, some people will argue, kind of outside of the scope that systemd should cover. But it's useful for me because basically, you know, the image that I specify here, the Fedora one, is like the default Fedora image, and I just wanted an easy way to actually test my stuff. There's another question. Oh, that's a very good question. So how you do actually generate these images? That's kind of out of focus for what we do. But my recommendation is always, you know, if you want to generate a suitable directory tree for Debian, you use the deb Bootstrap tool you might have heard of. It's basically a tool it's packaged even on Fedora, and it's packaged on Debian, of course, as well. And you just run it. And then we'll basically download everything from the Debian servers and drop them in one directory so that it can boot it up. Another way, like if you actually want to create an image, my recommendation would always execute a command like that will get you the default Fedora install, and then just work from there. So yeah, and then if you're creative, you could even use a Docker image and convert it, but that's kind of out of scope for my talk.